yesterday, what I want to do this morning is talk about the unspoken, try to give you an idea of where ideas come from. So let me have in at that. I can start with the conclusions. I consider the design, discovery, and growth of novel materials to be sort of the heart and soul of what I call new materials physics. This is synthesis combined with broad characterization tools and sort of a wide interest in a variety of novel states. And I think this is going to be where humanity finds the solution to its pressing problems. Either we discover the materials that help us out of the mess we're in, or we can have apocalypse, lose 90% of the population, 10% surviving, we'll have a better life. I'd prefer to find new materials. Because we need to find materials to solve energy problems, resource problems. Hopefully as a species we can do that. And what our charge, our task is to refine and utilize this tool in as many ways as possible and teach it to as many people as possible. So, for luck or for iron, we can start with horseshoes. And the reason I say this is, in politics, there's this theory called the horseshoe theory of politics, which says the political spectrum is not linear, where you have the far left and the far right. In reality, the far right actually can start looking a lot like the far left. Okay, and you're welcome to put whatever entities you want in here. You can choose your country. Tragically, many countries in the world are experiencing this right now. So, yes, it's a wonderful time. But I don't really want to talk about politics. I would say we also have a horseshoe theory of physics, where we can take the extremes of physics, exploratory synthesis, and closed-form theory, and in reality, these are much closer to each other than you really appreciate. I have theorists who tell me that it's trivial to go from an electron-photon superconductor to a neutron star to the quark-gluon plasma. You just change a prefactor in the Hamiltonian, and it's all the same. Trivial. Well, what is trivial, at least for me, is on the experimental side, I can take a simple structure, the half-Heusler structure, it's sodium chloride plus 1, simple cubic structure, and I can decorate this with different atoms. I can go from ti-nickel tin, which is a semiconductor, manganese nickel antimony, a ferromagnet, heavy fermion, non-centrosymmetric superconductor, topological insulator. That is trivial. You're just changing what you decorate, and you completely change the state. So these two extremes of physics are actually closer than you may appreciate. Now, I would say that we have an advantage. The advantage of synthesis over closed-form theory is, instead of just dreaming about things, we actually have our dreams become real. We can have physical reality. Well, you're familiar with the myth of Pygmalion, yes? Yes. Yeah, classical paintings. There, Rosa's embarrassed. Oh. All right. So, what do we try to do? We try to project a Hamiltonian onto the periodic table and actually grow substances. What do I mean by project a Hamiltonian onto a periodic table? Look, here's our periodic table, and if we think about this in terms of superconductors, light elements can give us tight bonding and high phonon frequencies. Transition metals can give us large density of states if we're thinking of a conventional superconductor, or possibility of tuning band filling or fragile magnetism if we have a non-conventional. If we substitute alkali or alkali earth for other valencies, this tunes band. By going up and down the Kacalginite or Pnictide column, we can tune bandwidth. Here we can have fragile moments or heavy fermions. Here we have local moments. These are all terms in a Hamiltonian that let us try to control superconductivity. Okay? So we can use the periodic table to steer around the physical phase space. But the problem is the number of potential compounds is huge. Okay? If I get rid of radioactive elements and noble gases, I still have 80 elements to play with. And if I do small combinatorial, okay, if I look at number of possible binary compounds, okay, and I give myself maybe 3 compounds per binary and ternary compounds, I have millions and millions of possible known or unknown compounds. And this is just too large of a phase space to play around with. So how do we choose what sample we want to make? Okay? In this talk, I want to give you an idea of how to coax the unicorn out of the forest, how to encourage visions of sugar plums to dance in your head, or if not sugar plums, maybe other more delightful or entertaining things, okay? So, I want to give you an idea of how to create and generate new ideas, and then how to make them manifest themselves, okay? So, in my own group, we have 3 ways to narrow this phase space, okay? And this is what I want to discuss in this talk, okay? Sometimes we want a specific compound, sometimes we want a specific ground state, and sometimes we want to search for known and unknown unknowns, okay? And I'll talk about each of these, okay? These are often overlapping, they often flow into each other, and I want to give you a sense of how this works, okay? So, let's start. I want a specific compound, okay? If I want a specific compound, this really reduces phase space. All possibilities become, I want a specific compound projected onto the periodic table as a delta function of the specific compound. See, I can do mathematics, okay? This is good. Often, the specific compound, if you choose the right one, is part of the birth of a new field, or, if you want a specific compound, there must be a reason you want a specific compound, okay? So, let me go over some examples of how this works, okay? Fine. It's worth noting in each of these cases, and I'll try to point that out, that as part of wanting a specific compound, we want it so much that we're willing to generate new technologies, new growth capabilities, new measurement capabilities to get us to that compound, and then these become part of the milieu that we work in. Okay, so 1994, there were 2 related superconducting compounds discovered. You had yttrium, palladium, 2 boron, 2 carbon, and lutetium, nickel, 2 boron, 2 carbon, quaternary compounds, and they had actually very good TCs. The yttrium palladium had a TC rivaling the highest non-high TC compound of the time. Okay, so we really wanted to try to grow these. Now, how do we do that? It's a tricky growth. Quaternary, as we saw yesterday, a quaternary phase diagram is no fun. Refractory, boron and carbon are incredibly high melters. Lutetium and nickel aren't that low. And it's incongruently melting. All right? Now, at the time, solution growth had been done. I'd been doing it, decanting at 700. For those of you who do solution growth, when I started doing this, decanting at 400 C was considered hot. I pushed it to 700, 800. This is when I pushed it to decanting at 1200. Okay, that's interesting. So what you can do is you can look at the nickel-boron phase diagram, and remember, we're growing out of liquids, and you have this cascade of eutectics. We have eutectics as low as about 1,000, okay? The nice thing is this means that we have a region that we can grow materials out of. What we were able to do is come up with this 2-step process where we could cool the 1221 and nickel-boron flux from 1,500 down to 1,200, and then reseal into silica and decant, and you can get lovely, nice crystals, and with lovely, nice crystals, you can do physics, okay? So we could study lutetium, nickel, 2 boron, 2 carbon. Here's the 17 KTC. It has a mildly anisotropic Hc2. It's not a very large Hc2. This is not going to be a practical superconductor. On the other hand, given that you could have it for lutetium, you can substitute in other moment-bearing rare earths. So you have lutetium or yttrium, but you also have thulium, erbium, holmium, dysprosium. For all of these materials, you have Tc, but for the thulium through dysprosium, you also have T-niels, and you can look at the interaction of magnetism and superconductivity. You can see Hc2 respond very strongly to the onset of magnetic order. There's a lot of neat physics you can play around with. This is sort of a standard evolution. We wanted a specific compound, but then quickly with the compound mastered, we wanted to study a specific ground state, superconductivity with magnetic interactions, and then often in basic research, there are surprises. In this case, the surprise was if you start looking at the small angle neutron scattering, which, as we mentioned yesterday, is a common way of modeling the vortex lattice. This was the first clean example of a hexagonal to square transition of the vortex lattice seen via neutron scattering. It was subsequently seen by some groups with tunneling microscopy, but these are not easy materials to cleave, and therefore you suffer a little. All right, let's look at another example. In 1997, we were interested in growing magnesium, rare earth magnesiums in quasicrystals, basically to look at what happens when you have a local moment embedded on an aperiodic sublattice. Okay? The problem was the samples were all polycrystalline and actually multi-phase. We were able to figure out what the phase diagram looked like. This is the compositional phase diagram. We could grow this out of excess magnesium and zinc. There was an exposed liquidus line that let us grow the quasicrystal. But since we're growing out of excess magnesium, this eats away at alumina, at silica. We had to develop a way of holding it. This is when we developed this 3-cap tantalum crucible, okay? Tantalum tube, you weld a cap in the bottom, you have a cap in between that you drill holes in to be the filter, and then you weld a cap on the top. This is done in the arc melter. This allows you to hold the material, you heat it up, you cool it, you decant, and you end up with single crystals that look like this, okay? This is, at the time, a remarkable single crystal because this was a macroscopic pentagonal dodecahedron. This clearly manifests the morphology of a forbidden crystallographic symmetry, 5-fold. This is what convinced a lot of people that quasicrystals actually were real. Okay? They should have believed the scattering data and the other things, but seeing something macroscopic helps convince you. Great. Now we have a pretty sample. We can do physics. We measured the magnetic properties. What happens is, with a rare earth on an aperiodic sublattice, we found that these were classic examples of spin glasses. Okay? It's not surprising you have a large degree of frustration because your nearest neighbor distances have a wide range of values on this aperiodic sublattice. You don't have periodicity, okay? So they were model spin glasses. With model spin glasses, you could ask sharp questions. So one of the questions we wanted to ask is there a difference between a Heisenberg and non-Heisenberg spin glass? The reason I pick on Heisenberg is gadolinium has no crystal electric field splitting. It has no local moment anisotropy. It's a perfect Heisenberg moment. The other rare earths will be non-Heisenberg. So I can look at the paramagnetic Curie-Weiss theta as a function of de Gennes scaling for all of these materials, the pure as well as an yttrium-terbium dilution and yttrium-gadolinium dilution. They all follow de Gennes scaling, which tells me the magnetic interactions are trivial. Very well understood. On the other hand, if I look at the freezing temperature versus theta, two measured parameters, this is my high temperature Curie-Weiss theta, this is the temperature at which it freezes at low temperatures, it breaks into two manifolds. I have one manifold for my Heisenberg, pure gadolinium, and this yttrium-gadolinium substitution series, and another one for my non-Heisenberg, all my other rare earths, and the yttrium-terbium dilution series. There is a clear difference, okay? Basically, the non-Heisenberg, the anisotropic moments freeze up at a significantly higher temperature. So, the trajectory, we really wanted a specific sample. We were then able to go to wanting to look at a specific ground state, and then we were able to play around with this idea of CEF and Heisenberg, non-Heisenberg symmetries. Okay? We're going to look at two more examples of wanting specific samples, and then we'll look at the other motivations. One of them, 2001, there were rumors that MgB2 might superconduct at 40 Kelvin. This was not announced, it was leaked. Jun Nakamitsu at a meeting on spin ladders and insulators said, oh, I think I've discovered a 40K superconductor in MgB2. No publication, no posting, no nothing. The internet worked. Those of us who are listening go, what the hell? So, is this real? Well, the first step to answering is it real is, can we make it? Okay. This is the magnesium-boron phase diagram. And unfortunately, after having spent all of yesterday hopefully impressing upon you, if you want to grow a crystal, you find the exposed liquidus line. There is no exposed liquidus line here. Basically, you have MgB2 existing with solid, liquid, and gaseous magnesium with no exposed liquidus. This is inauspicious for single crystal growth. On the other hand, and we tried lots of different ways, that's a different story. On the other hand, you can make polycrystalline samples very easily. And as a physicist, I'll take whatever sample I can measure. I prefer single crystals, but if I can't get that, I'll take high purity polycrystals. You can take high purity boron, magnesium, heat them up, as little as 950 Celsius using this tantalum tubing we developed for other magnesium growths. Okay? And the magnesium vapor diffuses into the boron and you get high purity MgB2. Hooray! And this is much better purity than what you buy from Alpha Azar or other things. That stuff has lots of oxides and impurities. This is the good stuff. Okay? Now, with that, we were able to take high purity isotopic boron, boron 10, boron 11. We see an isotope shift. It's a huge isotope shift. It's 1 Kelvin. Okay? We can see it in magnetization, in resistivity, in specific heat. This is the first published paper on superconductivity in MgB2. And with this first paper, we made it clear this was an electron-phonon mediated superconductor. Okay? Now, we can map out HC2 in these pure materials. It's actually fairly low. It's 15, 16 Tesla. Okay? The resistivities are fantastic. You have very large triple Rs. You have minor anisotropies. But just to sort of impress on the students, you don't have to have a single crystal to do good research. You can do a lot of good stuff with polycrystalline samples as well. Now, we wanted a specific compound, MgB2. We wanted to study the superconducting ground state, okay? We wanted to see if we could improve this, all right? And the reason I want to improve it is, here's niobium-3tin. Niobium-3tin is a well-known superconductor from the 60s, the late 50s. Okay? It has a TC of 17, and David Larblastier and co-workers optimized HC2 to be around 30 Tesla at low temperatures. Okay? Pure magnesium diboride has a higher TC, but the HC2 was low. Now, with a very pure BCS superconductor, in some cases you can actually improve HC2 by shortening the electronic mean free path. We were able to do that by adding carbon. With carbon, we weakly suppress TC from around 40 to around 35, but HC2 goes from 15 to 20 to 25 to 30 to 35. Okay? For 5% carbon substitution, we can have bulk superconductor that supersedes niobium-3tin at all temperatures. Okay? And this is significant because since 2001 or 2004, where we were able to do this optimization, okay, over the next decade, MgB2 has gone from, my goodness, what is that, to, yeah, and we're making stuff with it. Okay? Because this region, 20 Kelvin, for it to be absolutely operating well below TC with a large HC2 means that you can have a functioning superconductor that instead of having to be cooled by liquid helium can be cooled by helium gas. Okay? Makes it cheaper. Magnesium and boron are earth-abundant elements. Okay? It has a fairly isotropic HC2, and humanity has figured out how to make multifilamentary wires of MgB2, wind them into large coils, and actually make open access MRI units. Instead of being a solenoid as Helmholtz coils, you have MRIs made out of MgB2 at this point. Okay? All right. 2008, last example of one, a specific compound. We wanted to grow pure and potassium substituted barium iron 2 arsenic 2. Okay? Within 14 hours of reading Jorent's and Rotter's paper on polycrystals that they could stabilize superconductivity with potassium substitution in barium 122, we had grown single crystals. Okay? And the reason was you can grow them out of tin. Okay? In the same way we could grow cerium antimony out of tin or a terbium manganese antimony out of tin, we could grow barium iron 2 arsenic 2 out of tin. Here is the world's first large single crystal of barium iron 2 arsenic 2. Okay? We could substitute in potassium, get it to superconduct with a single crystal. You can measure anisotropic properties. Here's the anisotropic HC2 up to 14 Tesla, the field we have in our laboratory. And what's remarkable is 14 Tesla, which is not a small field, only suppresses TC from 30 to about 27, maybe 26. So HC2 is going to be big. In addition, it's looking fairly isotropic. Yes, isotropic. We went to the National High Magnetic Field Lab. We can measure it to fields around 60 Tesla, and what we can see is HC2 is increasingly isotropic, becoming less and less anisotropic, and if we remember, we were excited about 20 Kelvin in MgB2. For the potassium substituted iron arsenides at 20 Kelvin, our lower HC2 is in the order of 40 Tesla. What this meant is, within months of discovery of iron arsenide superconductivity, it was clear that these had the potential of being practical materials. Okay? HC2s are large, TCs are good. JC will always be the rate limiting step, but at this point, JC on some of these, and particularly the 1144s, is looking very promising. Okay? All right. Let's start looking at our other motivations more explicitly. Often, wanting a specific compound feeds into wanting a specific ground state or searching for new materials. Let me use the iron arsenides as a specific example, and then we'll explore these independently. Okay? So, first, let's look at wanting a specific ground state. Okay? Clearly, with the barium iron 2 arsenic 2, this was a new type of high TC superconductor. We wanted to know what the rules were. Okay? When does it exist? When doesn't it exist? How can I make it bigger? How can I make it smaller? Okay? Basically what that means is we could start with the barium iron 2 arsenic 2, and instead of iron, we could consider substituting in cobalt, nickel, copper, or manganese chromium. Okay? We don't need to limit ourselves to the 3Ds. We can go down to 4Ds or even 5Ds. Okay? Now, that means instead of having millions of compounds, if I'm just doing things randomly, I now am talking about a dozen substitution series. Okay? So I'm just trying to show you how you limit phase space. Okay? Now, with these growths, which is what kept us busy in 2008, we could understand the rules just empirically, Edisonianly, of how superconductivity worked in these materials. What was remarkable to me is we could substitute in cobalt, rhodium, nickel, palladium, and for isoelectronics, so if I look at cobalt and rhodium, I have virtually the same phase diagram for how I suppress the antiferromagnetic orthorhombic, for how superconductivity turns on. If I look at nickel, palladium, the same phase diagram, okay? Now, these two columns are not the same, but what's remarkable is if we look at the superconducting dome, it just scales with number of extra electrons. Here are the two domes for number of impurity atoms. They're quite separate, but when you just multiply this by a factor of 2, because these add 2 extra electrons as opposed to 1 extra electron, you see the same superconducting behavior. So the archetypical image of the rules of superconductivity in these materials is you suppress the orthorhombic antiferromagnetic transition. In many of these you actually split it, and this gives rise to this whole issues of pneumaticity. You can see superconductivity turning on as you suppress this transition and encourage fluctuations. You have a maximum TC near a putative quantum critical point, and then TC goes down on the overdoped side. Now, that was wanting to look at a specific ground state. You can also explore for unknowns, okay? This is an example of what I would call a known unknown. We have barium, we have strontium. What about calcium? What about magnesium? Okay? Barium and strontium were known compositions. Calcium and magnesium were not reported, okay? We were able to grow the single crystals of barium. We were able to grow single crystals of strontium, okay? It's sort of what I would call a clever monkey experiment. A clever monkey can figure this out. Let's try calcium. We discovered a new member of the 122 series, calcium iron 2 arsenic 2. We could grow, we discovered, and it's sort of rare to discover something in large single crystalline form, so we were happy, of calcium iron 2 arsenic 2. It's an extreme example of the physics we see in the barium and the strontium. We have a strongly coupled structural magnetic transitions. It's brutally first order. You can see both the orthorhombicity and the antiferromagnetism having hysteresis, having strong jumps at this transition temperature. We were able to look at the effects of pressure. We discovered a new type of phase transition called the Klepp's tetragonal. It was a lot of fun. It's ongoing, actually. We'll come back to this at the very end of the talk. Okay? Now, that's great. Calcium. What about magnesium? Well, we go up to magnesium. All attempts in our lab to grow magnesium 122 or to dope magnesium into calcium or anything else failed. I know at least 3 other groups around the world that made similar attempts. They found nothing also. So at least up to this point, magnesium doesn't seem to work, even when you try to grow it under 3 GPa's pressure. So it just doesn't like to form. Sometimes you reach the end. So sometimes you look for things and it doesn't work. All right. Now, let's move on to sort of the more interesting parts of the talk, because wanting a specific material is reactive. Okay? Either you discovered something and you really want it, or other people discovered it and you want it. Let's look at how you can try to want a specific ground state. Okay? This is an exercise in narrowing phase space, in negotiating with Mother Nature. Okay? And this negotiation lets you figure out where to find the materials you want. So, let's say I want a praseodymium-based heavy fermion. Okay? Let's see what that desire allows me to do. Okay? Now, praseodymium heavy fermion is not completely silly. You have heavy fermions with cerium and with ytterbium. Those are rare earths that have well-known ambivalency. Cerium can be trivalent and tetravalent. Ytterbium can be trivalent or divalent. You can hybridize the 4f electrons with the conduction electrons. Praseodymium is also a mixed oxide. It can be trivalent or tetravalent. Okay? The problem is praseodymium is a non-Kramer's ion. You do not have a guaranteed R log 2 degeneracy or entropy at low temperatures. I can have a singlet ground state. So if I want to have a doublet ground state, I need to do a little work. I can look at one of the most heavily referred to papers, probably from the Journal of Physics, Chemistry, and Solids, one of the most heavily referred to. It's Lee-Leeskin-Wolf, which is basically a compilation of how CEF levels evolve in cubic point symmetries for the rare earth. We can look at praseodymium. There's a gamma 3. It's a non-magnetic doublet. That would mean I would have some guaranteed entropy, okay? But I need a cubic point symmetry. So, let the negotiations begin. When I was doing this, Pearson's crystallography was in books. This is basically 7 volumes of books. More than 3 volumes on your lap starts to hurt, so you need to put them on the desk and other places, but you spread them out all over the place and have fun. And we can start negotiating. I want a cubic unit cell. I want a single rare earth site. I actually want the rare earth site in a cubic point symmetry. I want the rare earth to be praseodymium. These limit the number of compounds I can look at. Right? So, here is a part of a page of Pearson's crystallography. This is in the cubic materials. Here's CF16. CF16, I have the bismuth trifluoride. This is also known as the Heusler structure. And here we see silver 2 indium praseodymium. Okay, it was one of a few materials that had the cubic unit cell, cubic point symmetry, single rare earth praseodymium, and there was a little bit of literature. Rosemarie Galera in Grenoble in the late 70s, 80s, was looking for singlet ground state magnetism in praseodymium, looked at this, did inelastic neutron scattering to see the CF levels, and was disappointed because instead of a singlet ground state, it looked like a gamma 3 doublet, published a small conference proceeding and moved on. This is the hint that I wanted, that this might be exactly what I want. So we made it, we remeasured the CEF levels, we could confirm that we have a gamma 3 doublet, with about 6 MeV from the first excited state, so below 60 Kelvin, I'm in a singlet, I'm in a doublet ground state. We could measure specific heat. We could look at this in C or C over T at low temperatures. The high temperatures we could fit to the Schottky anomalies. The low temperature had a linear specific heat. If we plotted C over T versus T, it rises and saturates at 6 joules per mole K squared. That is a very heavy fermion if that's an electronic specific heat. So, can entropy be preserved to low enough temperatures for praseodymium to hybridize? Yes, but you have to be careful to preserve your entropy. Can praseo go heavy? Yes, but it's a different type of heavy fermion because this is a non-magnetic doublet. If you think of cerium or ytterbium, you have your local moments, and as they're fluctuating, they're being screened by a cloud of electrons. It's sort of this dynamic singlet. This has no moment. Instead, I have a non-Kramer's doublet that actually has the possibility of having a Jahn-Teller distortion. Okay? So I think what you're doing is you're dynamically screening this desire to have a structural phase transition. Okay? So, whatever, by having this negotiation with nature, we were able to come up with the first example, clean example, of a praseodymium-based heavy fermion. Now, let me give you a more modern version of wanting a specific ground state, okay? It employs the same ideas, but now we've gone into the modern age, so I'm actually using electronic tools, okay? Let's say I have the remarkable, unique idea of I want more high-TC superconductors. That's my idea, no one else thought of it, okay? Yeah, so, right. It's not actually all that profound, right? Look, here I have copper-based and iron-based. I'd like more of these. Now, just saying I want more, and I can go to my theorist, hey, I had an idea, I want more high TCs. You're a theorist, help me. And the theorist goes, okay, let's try to sharpen the question a little bit, okay? The question can be sharpened by saying, let's look at the high TCs that we sort of know and love. Here are the copper-based systems.